Okay, so before we do too much more with determinants here, I want to talk about a certain subclass of matrices here that are quite nice in a lot of ways, and those are triangular matrices. And there's two types of them. There's upper triangular and lower triangular. Right? So let's talk about an upper triangular matrix first. What an upper triangular matrix is a matrix that kind of looks like this. It has all these entries here. We have the main diagonal here, and all this stuff above the diagonal, right? But on this lower half here, it's all zeros. Right? So everything below the diagonal is a zero. Um, one way you can look at it is if the row number is bigger than the column number for the entry, then that entry is going to be zero. Right? Now we likewise have a lower triangular matrix. Right? Lower triangular matrix. And I'll give you a guess as to what that might look like. Right? We have A11. Right? Again, we have our diagonal A22, A33, ANN. Right? Let's see, this 21, A31, A32, A3N, oops, sorry, AN1, AN2, AN3, dot, dot, dot. Right, so again, everything on and below the diagonal this time can be whatever, but everything above the diagonal has to be zero. All right. So it's kind of like the opposite, right? It's actually essentially it's the transpose of an upper triangular matrix. Now, one thing I want to point out is these A's here in the upper triangular and lower triangular, they can also be zero. But the case for a triangular matrix is just that these are the only things not allowed to be zero. Yeah, so here we would basically say the same thing, except instead of below, it's everything above. Right? By the way, what if something is upper and lower triangular? What if something is both of these at the same time? So everything above the, or sorry, everything below the diagonal has to be zero, and everything above. Well, if you look carefully, that's exactly what a diagonal matrix, right? Because if everything above the diagonal is zero and everything below the diagonal is zero, then only things on the diagonal can be non-zero, and that's precisely what a diagonal matrix is, right? So, what do you think? These types of matrices will be really simple to do a determinant of. So, why is that? Well, let's talk about it for an upper triangular matrix. Right? So, let's do this. Let's copy this guy. Get that? So why are these matrices so great when it comes to determinants? Well, let's say A is equal to this. Okay. Then determinant of A, right? What we need to do is figure out how we want to do this. Now, if you remember, doing the minor and the cofactor expansion, we should pick a row or a column with the most zeros. Well, if we pick this column right here, only the first thing is not 0, right? So when we do the cofactor expansion, this is going to be A11 times the determinant of that minor, which is this. Right? But, oops, sorry here. Let's Control Z that real quick. Duplicate this. Right? But then we have the same problem again, right? Well, this first column again is one entry and then all zeros. So let's use that column to expand on. And again, this will be the only non-zero minor, just like before. So when we write it out, we have A11 times A22 times this determinant. But can you see where this is going? Now we have A33 and then a bunch of zeros below it. So this is just going to keep repeating until we run out of entries. And eventually we're left with A11, A22, A33, ANN. So for a diagonal matrix, the determinant is just going to be, or sorry, for a triangular matrix and diagonal as well, the determinant is just going to be multiplying the diagonal entries. So we'll call this a theorem. Okay. So for an n by n triangular matrix, A, the determinant of A is A11, A22, A33, just as many, it's just the product of the diagonal entries. Right, so this can be a 1 by 1, a 2 by 2, a 3 by 3, and so on. Right? So keep that in mind. The determinant of a triangular matrix is particularly nice. So coming up, when we talk about determinants and row operations, hopefully keep this in mind along the way. And then we'll see where that goes.